Scientific revolutions are relatively few and far between. Now, I've talked about a few of them. There was the great Copernican revolution of 1543, the discovery that planet Earth is not at the center of the universe. In fact, the title of the book by Copernicus on the revolution of the celestial spheres actually was the source of the word revolution in this context of radical change. We saw the Newtonian revolution. That's the recognition that motions on Earth and in space are governed by the same natural laws. And there have been equally profound revolutions in the life sciences, as we're going to see. But such revolutions are rare in science. Yet those of us who have been geologists for the past 30 years have seen just such a dramatic transformation of the earth sciences. We've lived through a revolution called plate tectonics. Now, the central principle of plate tectonics is that convection of soft, hot rocks in the Earth's deep interior causes thin, brittle plates of rock to move at the surface. In this lecture, I'll begin by setting the historic stage. I'll tell you about what the majority of geologists believed 50 years ago, as well as about the heretical and the rejected hypothesis of continental drift. Then I'll set out 6 lines of evidence that led slowly but inevitably to our current view of our dynamic planet. That's the theory of plate tectonics. Now, this evidence includes first the shape of the continents across the Atlantic Ocean, and then geological features that match up across the Atlantic Ocean. The third is the distinctive and non-uniform distribution of earthquakes and volcanoes around the globe. Then we have discoveries of seafloor topography, especially the Mid-Atlantic Ridge, and the ages of various volcanic islands in the Atlantic Ocean, and finally, the remarkable patterns revealed by seafloor magnetism. The basic premise of plate tectonics, that the Earth's continents are in constant motion above a mobile mantle, that was just inconceivable to geologists just half a century ago. But within a couple of decades, the overwhelming weight of evidence had convinced virtually everyone in the earth science community of this new paradigm, the theory of plate tectonics. Okay, the Earth is a dynamic planet. It's constantly changing and evolving. As James Hutton demonstrated, millions of years of gradual change lead to dramatic transformations of the Earth's surface. You know, even the largest earthquakes, they shift rocks by only a few feet, but given enough time, 2 blocks of rock can travel 1,000 kilometers past each other. Even the largest volcanic lava flows, they only add layers of magma that are a few feet thick along just one small part of a mountain. But given enough time, such layers can add up to a mountain tens of thousands of feet tall. So we have erosion, sedimentation, burial, uplift. All of these are gradual processes that seem to alter the landscape hardly at all over human lifetimes. But given enough time, the tallest mountain's going to weather away. The gentlest river is going to carve a deep valley. Constant, inexorable change is a hallmark of our planet. But as Isaac Newton showed, no change happens without a force. If the earthquakes and magma fountains then exist, then a force acting over distance and work has to be being done. And you can't do work without a source of energy. So what source of energy drives all of these changes? The answer to that question led to the plate tectonics revolution. That's the great change in earth sciences that has occurred almost entirely since the Second World War. This transformation in the earth sciences took place swiftly, rather quietly though, during many of our lifetimes. It's amazing how fast scientists adopted these bold new ideas. Now, as we'll see, the history of plate tectonics revolution reveals a lot about the nature of the scientific process. You know, when I was an undergraduate at MIT in the late 1960s, every textbook, every introductory geology course proclaimed that the Earth's oceans and continents were more or less permanent features of the globe. Here's a figure from one of my geology textbooks from my freshman year. Before the mid-1960s, it was conventional wisdom that mountain building was a vertical process. Mountains were thought to be like great rafts of relatively light, low-density material that were, in effect, buoyed up like an iceberg on the ocean. So mountains were thought to have very deep roots that balanced the relatively small projections above sea level with a very, very deep root. This whole buoyancy idea went under the general name of isostasy. It was said that mountains were in isostatic equilibrium. Scientists had lots of meetings on the subject, and there were elaborate calculations that showed how this or that mountain range formed. This prevailing view of vertical tectonics had a rather profound consequence. See, because geological forces were primarily up and down, it meant that geological processes were thought to be local and sort of idiosyncratic. So each country and each state had its own geological survey, and what was found in one region had relatively little bearing on any other area. That old expression, gold is where you find it, that seemed to be the basic geological wisdom for all kinds of geological resources and phenomena. So the study of the Earth's surface was hopelessly fragmented. It was balkanized, if you will. And the earth sciences were similarly fragmented into many subdisciplines. Earth scientists usually got an undergraduate degree in geology, but then they became highly specialized into the seemingly unrelated studies of fossils or volcanoes. You might be an economic geologist or an earthquake geologist. Some field geologists specialized in tectonics, that's mountain building and folding, while others were primarily concerned with the formation of granite or the effects of glaciers. I mean, how could the investigation of Welsh trilobites from the Cambrian era on one side of the Atlantic have anything at all to do with mountain building in New England on the other side of the Atlantic? And then there were geophysicists who studied the structure of the Earth's deep interior. But that research seemed to be totally unrelated to surface phenomena. And of course, scientists who studied oceans or atmospheres really seemed to be off in a completely different world. Now, this isn't to say that there weren't scientists who tried to find some kind of unity and connections. I want to tell you about one such effort. The theory of plate tectonics was preceded by the curious hypothesis of continental drift. That was proposed by the German meteorologist Alfred Wegener in 1912. Now, Wegener lived from 1880 to 1930. And his principal scientific work involved the upper air masses of the Arctic that seemed to drive some weather patterns in Europe. He died in Greenland while he was testing his theories. This was during his 4th polar expedition. Now, Wegener's theory of continental drift was predicated on several intriguing observations that had to do with striking matchups of geological features across the Atlantic Ocean. Now, the first suggestive piece of evidence is the shape of the continents, which are remarkably similar. If you look at a globe at North and South America on the one hand and Europe and Africa on the other hand, the sort of S-shaped coastlines seem to match almost exactly across the 3,000-mile wide ocean. Now, this is a feature that had been noted by mapmakers hundreds of years ago. For instance, this match was described by the English statesman and philosopher Francis Bacon, who lived from 1561 to 1626. And no one knew whether that was just a coincidence or whether it pointed to some aspect of a global mechanism. That's a tough call. You know, given the shapes of the continents and nothing else, how would you tell? How close would that match have to be to convince you that something is going on? But there's even more to this story. In addition to the matching coastlines, there are certain distinctive rocks and fossil localities that seem to match up exactly on opposite sides of the Atlantic. For one thing, you find a broad area of diamonds in streams and valleys of southern Africa along the west coast. And then you see similar diamond deposits in streams in South America near the east coast, just opposite. And then there's a very distinctive ridge of limestone outcroppings in southern Africa that matches a similar series of outcrops in the southernmost South America. And one of my favorite examples, this is a kind of trilobite. This is a big, wonderful trilobite called Paradoxites. And this is a complete specimen from Morocco, just to give you a sense of what this magnificent beast looked like. Well, you can go to a place named St. David's in South Wales and find a distinctive species of Paradoxites in cliffs right along the coast. Now, it's rather tough to get a complete one. In fact, I understand it's illegal to collect there now. But I was there in the early 1970s and found this specimen. It's fragmentary, but you notice it has the same central spine. It has these things coming off the tail. This is clearly the same kind of animal. And then there's similar deposits in New England that match up perfectly in this coastline jigsaw puzzle. Lo and behold, you can find the exact same critter. Here's a piece I collected in New England. Again, it's fragmentary, but you can see that it's quite obviously a Paradoxites. It has the same backbone, the same kinds of spines coming off it. So Wegener tabulated a bunch of examples of these transatlantic geological matchups. Again, you have to ask yourself, what's a coincidence? What's a real pattern? But you can confirm the observations. This is the great thing about science. You can go out and check the data yourself. You can actually reproduce Wegener's observations. Now, Wegener pointed to these starting similarities across the Atlantic, and he came to the bold conclusion that the continents had moved apart over hundreds of millions of years of geological history, and he called this idea continental drift. Now, Wegener's ideas had to give any geologist pause. The data he amassed were impressive, but there was a severe problem. The principal objection to Wegener's novel hypothesis was that it lacked any plausible mechanism for moving entire continents. Go back to Newton's laws. Nothing happens without a force. Force equals mass times acceleration. To move the immense mass of a continent would require an immense lateral force, a sideways force, and no such force had ever been observed. The geological community just wasn't ready to abandon years of research that seemed to validate the idea of vertical tectonics for Wegener's incomplete hypothesis. Now, to give you a sense of the resistance to continental drift, let me read you a quote from the distinguished American geologist Thomas Chamberlain. In the 1920s, he spoke for a lot of his colleagues when he said the following. Let me read this. Wegener's hypothesis is of the footloose type in that it takes considerable liberty with our globe and is less bound by restrictions or tied down by awkward, ugly facts than most of its rival theories. If we are to believe Wegener's hypothesis, we must forget everything which has been learned in the last 70 years and start all over again. So what actually caused geologists to forget everything that they had learned and start all over again? The plate tectonics revolution resulted primarily from the merging of 6 separate lines of observational evidence. And any one of these pieces taken alone probably wouldn't have led to the modern theory. But this is sort of like a lengthy legal proceeding. The eventual accumulation of an overwhelming weight of evidence tipped the balance in favor of plate tectonics. And here it was that Wegener clearly set the table. The oldest observational evidence for moving continents is clearly the shape of Africa and Europe as they fit into North America and South America. As I mentioned, the first question you have to ask is whether this match is just a coincidence. Early in this century, as more ocean soundings became available, the true extent of the continents was realized. You see, the land area we see extends out underwater along a gently sloping continental shelf. Then a very steep slope marks the beginning of the ocean basin. That continental shelf, which defines the true size and shape of the continents, often extends out hundreds of kilometers. And when you map out that full extent, the fit between the continents across the Atlantic is remarkably improved. In particular, take a look at this. The southern coasts of Africa and South America match almost exactly, even down to relatively small indentations and other features. Was this coincidence? That evidence made it seem much less likely. Now, much of Wegener's geological evidence was sound and intriguing. Major deposits of rocks and minerals and fossils did seem to match up exactly across the Atlantic like pieces of a jigsaw puzzle. I told you about the diamond deposits and the limestone formation and the trilobites, and there are other matching rocks and fossils as well. Again, you have to ask, at what point are these matchups more than just a coincidence? I do have to mention that one factor that delayed the acceptance of this idea was that most geologists weren't familiar with all the different kinds of evidence. Few people would have had appreciation of all the data on fossils and on sediments and on diamonds, not to mention the geographical and the language barriers that were associated with following the earth science literature of a dozen different countries on both sides of the Atlantic. Okay, now we come to a third line of evidence. That's the non-uniform distribution of earthquakes and volcanoes around the globe. Now, here you see this. Now I have to be honest, I suspect this evidence was really only applied to plate tectonics after other more direct approaches led scientists in the right direction. You'll see what I mean in a bit. Now, people have long recognized that some areas of the Earth are highly prone to earthquakes, while other regions seem quite stable. There are lots and lots of earthquakes in Los Angeles and San Francisco, but there are none in Houston or in New York City. Earthquakes occurred along long, obvious fracture zones like the San Andreas Fault, but also in bands around Japan, in the Middle East, in Chile, where there wasn't such an obvious fault system. And similarly, volcanoes, they occur in some places and not in others. There are lots of volcanoes in the Pacific Northwest, but none at all in the Midwest U.S. This so-called ring of fire here around the Pacific Ocean, that's an active belt of volcanoes. Going around clockwise from Washington and Oregon, that includes many, many volcanoes such as the Cascades, then the volcanoes of Central America and the Andes here, then almost all the South Pacific islands, the Philippines, Indonesia, Japan, and then the Aleutian Islands of Alaska. Now, in the mid-20th century, as more geological surveys were completed, as more seismic stations were established and more data accumulated, these distinctive patterns were refined. An important observation was that in many regions, including Japan and the Philippines, in the western coast of South America, strong earthquakes right along the coast and active volcanoes about 100 kilometers or so inland are found together. That's a very curious pattern. So whatever the mechanisms, it became obvious that some global process helped to dictate where earthquakes and volcanoes would appear. Now, a key piece of the plate tectonics puzzle came shortly after World War II. That's when the Navy declassified sonar technology, which had been used to track enemy submarines. Sonar works out by sending out a sharp sound wave, and you listen for an echo. I'm sure you've seen submarine movies where there's a sub-hunter and it sends out the ping. You get that echo, the ping, 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 ping. And as the sub gets closer, that echo comes back quicker. You know, ping, 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 ping. Well, sonar was easily modified to measure the topography of the seafloor. You just send down the sound waves and listen for the reflection off the bottom. And this technique led to an amazing discovery. Now, conventional wisdom in the 1950s was that the ocean floor was as flat and featureless as anywhere on Earth. They even called the deep ocean the abyssal plains. No one had any way to make depth measurements a mile or more down, so people just assumed there was nothing of interest to see. And then came the first sonar traverses of the Atlantic Ocean. Look at this. This is great. They revealed an astonishing chain of mountains called the Mid-Atlantic Ridge. This feature is the longest mountain chain on Earth. It runs north and south along the full length of the North and South Atlantic. The Mid-Atlantic Ridge lies almost exactly halfway between the continents, and it has that same sinuous shape that's closely parallel to the curving coastlines. Can you imagine what it must have been like to discover this feature? It's the longest topographical feature on Earth. It's more than 60,000 kilometers long. It's the biggest mountain range on Earth. And no longer could anyone suggest that the fit of the continents was just a coincidence. The discovery of the Mid-Atlantic Ridge and the subsequent widespread recognition was due in large measure to the American geologist Bruce Heezen, who lived from 1924 to 1977. Though he was trained as a paleontologist, Heezen spent much of his career at Columbia documenting ocean floor topography and preparing visually dramatic maps. And Heezen correctly recognized the Mid-Atlantic Ridge as what's called an extensional feature, where new crust was being formed. By the way, he incorrectly ascribed this extension to a gradually expanding Earth. Well, following Heezen's work, similar ridges were found elsewhere, including one just a few hundred kilometers off the coast of Washington and Oregon. That ridge was just a day's sailing from major oceanographic facilities in Washington State and in Oregon, so it's become the best studied ocean ridge system of all. It was also documented that these ridge systems were composed of recent volcanic rock. So the ridge is volcanic, and the volcanoes are still active. Now, that was quite a surprise, too. By the way, I have to add a personal note here. Heezen, he died at sea in 1977, and at the time he was quite famous. About the early 1970s, when I became a graduate student, I began to notice that many senior geologists were very friendly to me, and a number of them would call me Bruce from time to time. I've never mentioned this to anyone before this, but I now suspect that some of these people may have confused my name, Bob Hazen, with Bruce Heezen. At least they may have thought I was somehow related, and I wonder how that coincidence may have actually helped my career in those early days. Well, anyway, following Heezen's work, Princeton geologist Harry Hess contributed a seminal paper on ocean floor spreading. He described the mid-ocean ridge as places where new ocean crust is forming and spreads out laterally. That's a mechanism that could explain the opening of the Atlantic Ocean. You see, as new crust pushes outward, it could carry along the continents like a conveyor belt. The mechanisms of this process were still awfully fuzzy, but geologists were getting close to plate tectonics. And then we come to the fifth line of evidence. That's the age of volcanic islands in the Atlantic Ocean. These ages provide yet another clue. Now, radiometric techniques were used by geologists to date rocks from islands such as Iceland and the Falklands, the Canaries, the Azores, and so forth. In 1964, John Tuzo Wilson, who was a Canadian-born geologist working at Princeton, found a striking trend. Turns out that islands that lie close to the Mid-Atlantic Ridge are relatively young. Iceland, which lies right along the ridge, is still erupting after all. But islands far off the ridge, on the other hand, are much, much older. The Falklands are about 100 million years old. So Wilson made this plot of distance from the ridge versus age, and he found that you get an almost linear trend. Now think about what that means. Islands on the ridge today are erupting. Islands close to the ridge are relatively young. Islands farther from the ridge are much older. And that pattern is symmetrical about the central ridge. The data seem to support Hess's idea that the Mid-Atlantic Ridge is the place where new crust is formed and gets pushed out to either side. And then we come to the sixth and the most convincing piece of evidence, the smoking gun of plate tectonics. This evidence came from seafloor magnetic data. Now, sensitive ocean magnetometers, once again, these were developed by the Navy to find submarines. They were declassified in the 1950s, and they were used to measure the magnetic orientation of rocks on the ocean floor. See, volcanic rocks usually contain small amounts of magnetic minerals, especially a mineral called magnetite. Recall that magnetite crystals can act like little compass needles. They tend to become aligned with the Earth's magnetic field. And when the molten rock cools, the magnetite freezes in the orientation of the Earth's magnetic field. So the cooling rock retains a record of the field at the time when it was formed. So oceanographers can measure this frozen magnetic field by dragging a magnetometer across the seafloor behind their ships. The magnetometer glides along and records variations in Earth's magnetic field that result from the slightly magnetic rocks. Now, it's a tricky measurement, but it can be done. Okay, and here's what they found. Astonishingly, as ships sailed across the ridges, the magnetic orientation of the rocks kept flipping back and forth by 180 degrees. You'd be going along for a while, and the rocks would appear to be magnetized in the normal orientation like today's field. But then you come to an area where the volcanic rocks were magnetized in exactly the opposite direction. North and south magnetic poles were flipped around. This was totally unexpected evidence that the Earth's magnetic field reverses from time to time. That in itself is remarkable. It relates to instabilities in the liquid outer core. But here's why this is important for plate tectonics. Look at this. American oceanographer Drummond Matthews and the British geophysicist Frederick Vine found that if you mapped all these areas of normal and reverse magnetism on the ocean floor, you get long strips that are parallel to the ridge, and they're symmetrically disposed about it. Look at this figure. This is their original data on the Juan de Fuca Ridge. You can see the parallel and symmetric magnetic regions. Vine and Matthews reported this data in the September 7th, 1963 issue of Nature. Their article was entitled Magnetic Reversals Over Ocean Ridges. Many historians point to this single paper as the turning point in plate tectonics. The symmetrical stripes of magnetic rocks clearly show the conveyor belt mechanism moving rocks out to either side of a ridge. Here's a schematic diagram of what's happening. The ocean ridge is in the center. That's a place where volcanic magma keeps getting pumped to the surface. This new rock piles up along the ridge, but it can't just do that forever. So the crust moves out to either side like a two-sided conveyor belt. So you can see two key features here. First, the material's older the farther away you get from the ridge. That's why the ages of volcanic islands get older the further they are from the ridge. Also, you can see why the stripe patterns are symmetrical. The Earth's magnetic field is normal for a while, then the rocks move out symmetrically with the normal magnetic orientation. And then the Earth's field flips, and a new stripe forms with opposite orientation. This resulting pattern is parallel to and symmetrical about the ridge. Now, perhaps the most influential article of this early formative period of plate tectonics was by Vine and Tuzo Wilson. It appeared in Science in 1965, and it presented the case for moving continents in the data of all this accumulated data. Now, I remember hearing a seminar by Wilson on this subject while I was an undergraduate at MIT in the 1960s. And I especially remember him talking about the age of volcanic islands, because rock dating was a really big deal at MIT. There was a whole rock dating lab, and volcanic rocks were a specialty there. I know it's easy to romanticize such events, but my recollection is that the audience was absolutely rapt, and that many of the scientists present seemed to become convinced of the truth of plate tectonics. Wilson was a really persuasive speaker, and these ideas, of course, have been floating around for a while. But I find this friendly reception especially astonishing, considering that many of the faculty had been teaching the old theories for decades. In fact, I'm quite sure that some of them had been teaching about isostasy and vertical tectonics that very semester that he visited. It would have been really easy for professors to reject revolutionary ideas that dismissed a lifetime of their own research. But in science, some new ideas just feel right. They come along at the right time. They resolve long-standing problems in a neat and elegant way. And so the acceptance of plate tectonics theory was swift, and it was overwhelming. The few key remaining problems were quickly solved by an army of scientific converts. The textbooks, they were rewritten. Old data were reinterpreted in light of this powerful, new, all-inclusive theory of the Earth. And I'm emphasizing the nature of this intellectual transition for a reason. See, contrary to some popular characterizations, scientists aren't closed-minded. They're not that conservative. They aren't adverse to changing theories and accepting new ideas as long as the evidence warrants change. So if scientists reject the premises of astrology or remain non-committal about the reports of UFOs, or if we scoff at so-called scientific evidence for the occult, it's not because we're rigid and closed-minded. It's because of a lack of reproducible data. Indeed, every scientist I know loves new ideas because new ideas lead to new research opportunities. That's one of the joys of science. You know, I've talked a lot about evidence for plate tectonics, but I haven't really described in any detail what the theory says. I'll go on to a lot more detail in the next lecture, but let me give you a brief overview here. We've seen that plate tectonics describes a process by which new crust is continuously being formed at mid-ocean ridges. But if new crust is continuously formed at the mid-Atlantic ridge and elsewhere, where does the old crust go? The Earth is certainly not expanding, as Bruce Heezen suggested. So if new crust appears one place, it better disappear someplace else. This was an immediate and an obvious problem for all the early work on ridge spreading, and it quickly led to a solution that relates directly to that earthquake and volcano evidence I told you about earlier in this lecture. Look at this. We now understand that the Earth's surface is broken into about a dozen tectonic plates. These are relatively thin, brittle slabs of rock that are no more than a few tens of kilometers thick, but up to thousands of kilometers across. The movement of tectonic plates is accomplished by three types of plate boundaries. Now, we have divergent boundaries. As we've seen, the Mid-Atlantic Ridge is an example of one of these divergent boundaries. This is where new crust is formed. This crust moves away from both sides of the ridge like material on a broad conveyor belt. Thus, you get magnetic stripes that are parallel and symmetric about the ridge, and volcanic islands, which are farther from the ridge, are going to be older. Okay, and then look at this. Old crust is taken back into the mantle at convergent boundaries. This process is called subduction, and it occurs in those areas around the Pacific Rim where you find coastal earthquakes and inland volcanoes that occur close to each other. You see, the earthquake happens where the plates converge right here, and the volcanoes occur some distance inland because the subducting plate partially melts as it goes down into the Earth. That's over here. And then a third type of plate contact called transform boundary occurs where two plates slide against each other. The San Andreas Fault is an extensive transform boundary that divides California at the junction of the North American plate and the Pacific plate. Okay, so that's a bit about the geometry of plate tectonics. But what about the source of energy that powers the movement of entire continents? That was a really big question. Geophysicists quickly realized that the only energy source large enough to generate such a force is the Earth's own internal heat. And here you need to know two things. First, we have the laws of thermodynamics. Heat moves from hotter to cooler regions, so the Earth's interior heat wants to get out. Heat can move by conduction, which is pretty inefficient, convection, which is a lot more efficient, and radiation. The second point is that studies of rock mechanics revealed, this was in the 1950s and 1960s, that at the elevated temperatures and pressures of the Earth's deep interior, lots of rocks become relatively soft and plastic. Rocks in the mantle can actually flow, albeit very slowly and over long periods of time. So we now realize that plate motions are driven by the convection of hot plastic rock in the Earth's mantle. This is the second law of thermodynamics at work. The development of this convincing underlying mechanism for plate movements assured the almost universal acceptance of plate tectonics. The theory of plate tectonics had tremendous power and appeal, and as much as anything, the theory is attractive because of the way it unifies geological studies that were isolated both topically and geographically into one global science. The theory successfully synthesized all sorts of data from lots of different subdisciplines. For the first time, oceanographers and paleontologists, the economic geologists, the geophysicists, the field geologists, and in every part of the world, they had a common paradigm. All of a sudden, studies of fossils were critical to understanding mountain building. Studies of the distribution of volcanoes led to vast new ore deposits. And the field geology of whales had an immediate relevance to field studies in New England. After all, Wales and New England were once connected to each other. The theory of plate tectonics integrated the earth sciences as never before. Meetings of big earth science societies had a new vibrancy. More than ever before, geologists had a great excuse to travel to every corner of the globe. As we'll see, the theory of plate tectonics went beyond geology. The theory provided new ways to analyze data on paleoclimates and on glaciation, and it radically changed ideas about the evolution and distribution of life on the planet. And most important for a scientific theory, plate tectonics made specific, testable predictions about the dynamic Earth. In summary, this lecture introduced the overwhelming evidence that led to the idea that the Earth's surface is divided into several thin, brittle, mobile plates. That's the theory of plate tectonics. I outlined 6 lines of evidence: the shape of the continents across the Atlantic, geological features across the Atlantic, the non-uniform distribution of earthquakes and volcanoes, seafloor topography, especially the Mid-Atlantic Ridge, the ages of volcanic islands in the Atlantic, and then finally seafloor magnetism. Eventually, the overwhelming weight of evidence convinced the entire earth science community of this new paradigm. And in the next lecture, we'll explore some of the consequences of this revolutionary theory.